Let's imagine a space with absolutely nothing in it. No air, no friction, no wind. If we drop a solid iron sphere into this perfect void, it yields to the only force left in the room, gravity. Here, gravity functions as a rigid mathematical constant. Every single second that iron sphere falls, its downward speed increases by exactly 9.8 meters per second. We actually tested this on the moon. In a true vacuum, that constant rate of acceleration applies to a heavy iron sphere, a feather, or an astronaut in exactly the same way. The mass of the object doesn't matter. Stripped of all outside interference, gravity dictates motion absolutely. It creates a flawless, perfectly predictable physical system where every falling object obeys the exact same rule. So, what happens if we reverse the tape? If that same iron sphere is thrown straight up against gravity, it smoothly decelerates until it hangs motionless at its peak for a split second. This chart plots the object's path. In a vacuum, gravity bleeds off the sphere's upward speed at that exact same constant rate of 9.8 meters per second squared. Once the sphere peaks and falls, gravity adds that speed back at the very same rate. Because the environment is pristine, the kinetic energy the sphere has when it leaves your hand is perfectly conserved. It returns to your hand with the exact same amount of energy it left with. But this mathematical perfection doesn't exist outside of a vacuum chamber. We live at the bottom of an ocean of fluid, the atmosphere, and that changes the math entirely. Step outside, and that falling iron sphere has to push millions of air molecules out of its way. This creates aerodynamic drag. Unlike gravity, which always pulls straight toward the center of the Earth, drag always points in the exact opposite direction of wherever the object is moving. As the object forces its way through the fluid, drag continuously strips away its mechanical energy. That kinetic energy is converted into microscopic thermal energy, heating up the surrounding air. The atmosphere functions as a relentless tax on movement. Every inch the sphere travels, it has to pay a toll, ensuring that the theoretical symmetry of our vacuum chamber is physically impossible in the real world. Let's throw that sphere upward one more time, now factoring in that atmospheric tax. On the ascent, gravity and drag both pull downward. These forces stack, causing an aggressive deceleration that forces the sphere to stop at a lower peak altitude. On the descent, gravity still pulls down, but the drag vector flips to point upward, fighting the fall. Because the object spent its upward journey losing energy to the air, it has less kinetic energy to work with on the way down. Combine that with drag pushing up against it, and the sphere travels slower, on average, during its descent than it did during its ascent. Since it covers the exact same distance, but at a slower average speed, the trip down takes longer. The time of descent is strictly greater than the time of ascent. The temporal symmetry of gravity is permanently broken. If we lived in a vacuum, a falling object would accelerate endlessly, reaching catastrophic speeds by the time it hit the ground. This graph illustrates how air resistance solves that problem. Drag isn't linear. As an object falls faster and faster, the air resistance pushing against it grows proportional to the square of its velocity. The drag curve sweeps aggressively upward the faster the object moves. So at what exact moment does an object hit its absolute speed limit, its terminal velocity? It happens when the object falls fast enough that this rapidly growing upward drag vector perfectly matches the length of the constant downward gravity vector. The two opposing forces cancel each other out. This creates a state of dynamic equilibrium. The net force on the object drops to zero, acceleration completely stops, and the speed is permanently capped. When you look at the human stakes, this physical speed limit makes skydiving, or a capsule re-entering the atmosphere, survivable. Terminal velocity is the atmosphere's defense mechanism against gravity. The universe might constantly try to pull us down, but nature always resists motion.